In this video, we're going to take a look at series, and specifically we're going to look at the geometric series, the harmonic series, and the test for divergence. So in this first example, we have the sum from n is equal to 0 to infinity of 3 over 2n. And this is a geometric series, and the form for geometric series is the sum from n is equal to 1 to infinity of a r to the n minus 1. And if the absolute value of r is less than 1, then we're convergent. And if it's greater than or equal to 1, then we're divergent. And if your geometric series is convergent, it's going to ask for a sum. And the formula for a geometric sum, so geosum, is a, and a is your first term, divided by 1 minus r. So we're going to need that as well if we're convergent. So in this first example, I'm going to rewrite this as the sum of n is equal to 0 to infinity, and then 3 times 1/2 raised to the n. And remember, 1 to the n is just 1, regardless of what number n is. So now that we have this written, our r value here in this problem is 1/2. And since it's less than 1, we're convergent. And because we're convergent, we're going to find the sum. Now, in order to find the a value, since our sum starts at n is equal to 0, if we plug 0 in for n, we would have 1/2 to the 0, which is 1. So 3 times 1 is 3. So a is equal to 3. So we have 3 divided by 1 minus. Now we have r is equal to 1/2, and that is equal to 3 divided by 1/2, or 6. So our geometric series here is convergent, and the sum is 6. Now when you have multiple pieces here, like we do in this next example, we have the sum of n is equal to 0 to infinity, and we have 5/4 n plus 1 over 3n. Now in 5/4 raised to the n, r is equal to 5/4, and that is greater than 1 or equal to, so we're divergent. And if one of the pieces is divergent, the whole thing is divergent. And because it's divergent, we can't find a sum, so we're finished with this problem. So even though 1 over 3n we can rewrite as 1/3 all raised to the n, and this piece would be convergent, the first term is divergent. So we're done with that problem. Here in the harmonic series, we have the sum n is equal to 1 to infinity of 1 over n, and this is divergent. So there's no real example because this is a special case. 1 over n is divergent, and we call this the harmonic series, and we'll use this later on in this chapter. So for the test of divergence, what we're going to do is we're going to take the limit as n goes to infinity, and if the limit as n goes to infinity of a sub n is not equal to 0, then it's divergent. So we're going to take the limit as n goes to infinity of 3n minus 1 divided by 2n plus 1. So we're going to divide everything by n. So we have the limit as n goes to infinity. 3n divided by n leaves me with 3, minus 1 over n divided by 2n divided by n is 2, plus 1 over n. So both 1 over n terms go to 0 when we take the limit to infinity, and that leaves us with 3/2. So we are divergent. It's important to remember that when using the test of divergence, you can only prove that it's divergent. So if this limit is equal to 0, that doesn't necessarily make it convergent. And the last example I want to look at is finding the values for x that make this series convergent. And here we have a geometric series. We have the sum from n is equal to 1 to infinity of x to the n divided by 2 to the n. And we can rewrite this as x divided by 2 all raised to the n. In order for this to be convergent, we need the absolute value of r to be less than 1. So our r value here is equal to x over 2. So we need the absolute value of x over 2 to be less than 1. So here we can pull the 1/2 out of the absolute value because it's positive. So we can say 1/2 absolute value of x is less than 1. And now multiply both sides by 2. So the absolute value of x is less than 2. So our x value can be -2 less than x less than 2. So in between -2 and 2, but not including either number. And that's this video on series.